If we already know our distance and time measurements are not something that we can transfer between frames, it shouldn't be a surprise that we'll disagree about velocities if we're in different inertial frames. If I think your clock is wrong and your meter stick is wrong, I can't trust the velocity you claim to measure using them. Your book goes through the derivation of this from the Lorentz transformations. We can go back to the baseball thrown from a train, and we can say if the velocity of the train relative to the ground is VAB, and the velocity of the baseball relative to the train is VBC, that the velocity of the ball relative to the ground, VAC, is just the sum of the two. Einstein says instead of that, we take the sum and then divide it by 1 plus the product of the velocities divided by c squared. Now, when we put in our 35 and our 20 meters per second for the train and 15 for the baseball, the difference between the Einstein answer and the Newtonian answer of 35 is about 10 to the negative 13 meters per second. So again, it's a ridiculously small correction, completely negligible at this velocity. This is kind of like the way we don't need to calculate the gamma factor, even for an astronaut on the space station moving at 7,500 meters per second. If we want to calculate that, we have a high precision calculator that will do it. We get about 3 parts in 10 billion for the difference between the gamma factor and 1. So this would mean two identical twins, one of them traveling at that speed would age a tenth of a second less over 32 years than the other one. So it's completely unimportant. On the other hand, if we go to faster speeds, let's say our train is moving at 0.8 c and we fire a bullet towards the front at 0.5 c. Newton says somebody on the ground would measure 1.3 c for the bullet. Never fall for this on a test. You should never get a speed greater than c for any single moving object. If we use the Einstein method of addition, we get 1.3 c divided by 1.4, or 0.92857 c. So certainly faster than either of the two component velocities, but not equal to their sum. Less than c, which is what we expect. On the other hand, what if we use a flashlight instead of a gun? The flashlight's velocity, the light would be c. We go through the same math, and this time we get c, which is just what our second postulate told us. What if we do it the other way and fire the flashlight off the rear of the train? What would someone measure for that speed? We go through the same thing. Now we change the sign of c because the light is going backwards relative to the train, and we get negative c. So we still get the speed of light measured the same by all inertial observers. Now, other things we notice about motion, we could include the Doppler effect here. You may not have done this in Physics 1 because it's one of the things that you usually don't have time to get to, but you've certainly experienced it when you hear an emergency vehicle race towards you and then away from you. You hear the pitch of the siren change because the fire truck or ambulance or whatever is moving a decent fraction of the speed of sound. Interstate speed is about 10% of the speed of sound. The Doppler effect for light, we explain it similarly, but it's simpler. And the reason is, with light, all that matters is relative motion, while for sound, you get different results depending on whether the source is moving or the observer is moving. The reason there's a difference is, there is an absolute standard of rest for sound. We have to have the air to have sound in it, and that gives us a frame of reference. So whichever one of you is moving will actually feel wind in your face. It's not a symmetric situation the way it is for light. So in this picture below, imagine this green face is emitting flashes periodically, every fraction of a second, while moving to the right. The red, blue, and yellow faces are all at rest with respect to each other, and they're moving with respect to the green face. The oldest circle is this largest one. It was emitted when the green face was at the center, and it's expanded out to this current red size. As the circles get younger, they're smaller because they haven't had as long to expand, and their centers are moving to the right because that's where the green face was when they were emitted. If you look at this, you notice at the blue face, he's about to see many, many blips compressed into a short time. He's going to see a higher frequency of flashes. And the red face, on the other hand, these these flashes are getting stretched out, he'll see a lower frequency of flashes. This is the regular Doppler effect. The blue observer would see green light push towards the blue end of the spectrum, shorter wavelengths, higher frequencies. The red observer would see the green light push towards the red end of the spectrum, longer wavelengths and shorter frequencies. The math is reasonably straightforward. All we need to know is what's the relative velocity as a fraction of the speed of light, and we can see this is our difference between our observed wavelength and the one sent by the source. We define v greater than 0 as moving away from the observer and v less than 0 as moving towards the observer. The yellow face, though, is different. If we were looking at sound, we could imagine the yellow face is at the center of a circular racetrack and the green face is moving around it in a perfect circle, never getting any closer, never getting any farther away. So the green face and the yellow face will hear the same sound. In this case, though, we know that there is relative motion between the two, and there will be the regular relativistic time dilation where the yellow face sees the green face's clock as slower by a factor of gamma. That means the frequency is lower by a factor of gamma. This is called the transverse Doppler shift, and we just take the source frequency and divide by gamma. This is purely relativistic. We don't see anything like this for sound. There also have to be changes in momentum and kinetic energy, and here's how we can figure that out. Let's say our two twins that we put on the rockets are grown up and fighting. Each has a rocket, and they're headed towards each other at relativistic speeds. Again, we don't say which one is moving because the question doesn't make any sense. We just know there's relative motion between them. As they pass close by, each one is going to try and throw a punch, and notice that's perpendicular to the direction of motion, at the other one. We know if the fists touch that by symmetry we can't have the green one win or the orange one win. It doesn't make any sense. We can't pick a winner out of the information that we have. So what has to happen is the punches have to bounce off of each other and carry equivalent momentum. This is going to be confusing to each twin because they will see their own punch as moving fast, and on the slower other twin ship, they'll see their arm moving much more slowly. How do they explain the fact that that slow punch was able to carry the same momentum as their much faster punch? The way Newton would explain it, or might explain it, would be to guess that since the momentum was the same but the velocity is smaller, there must have been a change in mass because of the motion. So if P equals mv, we can say that we know that time and length both change by factors of gamma when they're measured by a moving observer. We could say maybe mass does the same thing. It changes by a factor of gamma, so that there's a rest mass, m0, that you would measure for things in your frame, and a relativistic mass, m0 times gamma, that you would measure for things that are moving. We already have the idea of proper length and proper time for things you measure in your own frame, and then we have the relativistic versions involving gamma. So this would just be adding one more thing to that list, a proper mass. This would fix it, and there's a strong tradition to sort of do the minimum damage to equations when we discover new physics. For example, in Physics 1, when we tried to do Newton's laws in an accelerating reference frame, rather than changing Newton's laws, we said, how about if we introduce centrifugal force, this fictitious force that pulls you to the outside of a curve? Pretending that that exists lets us solve problems at accelerating reference frames. Just this semester, when we looked at AC circuits, remember we had two different power formulas. We had P equals IV for DC circuits, and then for AC circuits we had P equals I max V max over 2. What we decided to do was create the RMS current and voltage, because then we get to use the same P equals IV formula for everything. So that was the idea behind this relativistic mass. We can preserve P equals mv, the Newtonian expression for momentum, but we change the expression for mass from m to m equals m0 gamma, so that our momentum is m0 gamma v. The only problem with this is mass doesn't really change. It's an invariant that everybody has to agree on. And for this and other reasons, there's pretty much no modern physics textbook that will talk about relativistic mass or rest mass. They'll just talk about the mass. Unfortunately, if you get a what you'd call a popular book on relativity, what they would have at a bookstore, they'll still have this idea in it sometimes, and it's just really better to do without it and say, you know what, we learned the wrong formula for momentum in physics 1. What we should have learned is mv gamma. I should probably say incomplete rather than wrong, because mv works incredibly well for practically everything. But when we do get to relativistic speeds, we need to use p equals mv gamma. At low speeds, of course, gamma is essentially 1, and we're back to what you learned last semester. And notice we don't have an M0 here. We're never going to talk about rest mass and relativistic mass, all that again. There's just going to be mass. Now, we changed the formula for P, so do we need to go back and redo everything in that chapter of the book? Well, even for things like bullets, satellites, and things, we've already figured out gamma is incredibly close to 1. Newtonian physics is good enough for almost everything, so really we should say it's incomplete rather than wrong. This new expression for momentum also explains why c is the ultimate speed limit in the universe. If we want to accelerate things, we exert forces on them. That force increases their momentum, but as we can see, we can increase momentum without changing velocity or mass much at all. For low speeds, we get the Newtonian result. If I have a 1 kilogram mass moving at 100 meters per second, I have to increase its speed to almost exactly 200 meters per second to double its momentum. On the other hand, if a 1 kilogram mass is moving at 0.99 c, I can find its momentum with mv gamma and get this 7.088 times 0.99 c. That would be the momentum. However, if we bump up the velocity to 0.9975 c, gamma is now 14.15, and we pretty much doubled the momentum, but we've only increased the speed by 0.8%. This is more dramatic at higher speeds. If we go to 0.9994 c, we double the momentum again, and the velocity change is now only 0.2%. We can never change the momentum enough to bring the velocity to c. This also means we're going to have changes in the energy expression. Your book figures this out by using the work energy theorem from last semester. If we don't have friction and we don't have opposing forces, so we don't have a potential energy, we get that Ke is just integral of f dot dx. If we go through the math like they do in your book, we are left with kinetic energy as gamma minus 1 times mc squared. Now, this needs to go back to our old expression if the speeds are small. What we can do here is write gamma as 1 over square root of 1 minus beta squared and ask Mathematica to do a series expansion for us around the zero speed limit. We look at the terms here and we have to figure out how many do we need to keep. If we only keep the first term, that's literally zero speed and we don't get anything out of that. So we have to keep at least this term. We justify getting rid of these others because if b is already very small, b squared will be small, b to the fourth will be super small, and it'll just get worse. So we decide we'll keep the b squared part, and what that gives us is Ke is gamma minus 1 mc squared. We put in our expansion here, 1 plus beta squared over 2, and we get beta squared over 2 mc squared. We know beta is v over c, so we get that kinetic energy is pretty much 1/2 mv squared as expected. So we can do a whole lot of work on a particle and its kinetic energy will increase in proportion to that, but its velocity will not.